Welcome to G Fun Facts Online. Today, we're journeying to the frozen frontiers of our solar system. Far beyond Mars, orbiting the gas giants Jupiter and Saturn, are worlds once dismissed as cold, dead rocks. But we now see them as prime candidates in the search for life beyond Earth. Why? Because beneath their kilometers-thick shells of ice, we believe there are vast, global oceans of liquid water. The key to unlocking these hidden seas, and potentially one of humanity's greatest discoveries, is a technology that lets us see the unseen: radar. We're going to dive into how this technology is revolutionizing our understanding of these enigmatic moons, and bringing us closer than ever to answering the question, are we alone? The outer solar system is teeming with icy moons, but a few stand out. These are worlds where the gravitational tug-of-war with their colossal parent planets generates enough internal heat to keep water liquid. This process, called tidal heating, creates potentially habitable environments, despite surface temperatures hundreds of degrees below freezing. Let's meet the main suspects. First up is Jupiter's moon Europa, perhaps the most famous ocean world. It's about the size of our own moon, but its surface is a bizarre landscape of cracks and ridges, and it's almost completely free of large craters. This tells geologists that the surface is young and constantly being reshaped from below, likely by the ocean churning beneath it. The biggest clue came from NASA's Galileo mission in the 1990s. Its magnetometer detected a magnetic field around Europa that could only be explained by a global layer of something electrically conductive, like a salty ocean. It's estimated this hidden ocean could hold more than twice the water of all of Earth's oceans combined, buried under an ice shell maybe 15 to 25 kilometers thick. Then there's Saturn's tiny moon, Enceladus, the little moon with a big surprise. In one of the most stunning discoveries of modern space exploration, the Cassini spacecraft flew past Enceladus and saw something incredible: massive plumes of water vapor and ice crystals erupting from deep cracks near its south pole, nicknamed tiger stripes. These geysers are spewing material directly from the subsurface ocean into space. It's a free sample. Analysis of this material has already found water, salts, and even complex organic molecules, the very building blocks of life. Jupiter has another giant moon, Ganymede, the largest moon in our entire solar system, even bigger than the planet Mercury. It too is believed to have a subsurface ocean. But what makes Ganymede so fascinating is the idea that it might not be a single ocean. Data suggests a structure more like a planetary club sandwich, with multiple layers of ice and liquid water stacked on top of each other. This complex internal plumbing could have profound implications for its potential to harbor life. Finally, let's not forget Saturn's largest moon, Titan. Titan is a world unlike any other, with a thick, hazy nitrogen atmosphere and lakes and rivers of liquid methane on its surface. It's a hydrocarbon wonderland. But beneath all that, data from the Cassini mission strongly suggests a deep, global ocean of liquid water. The combination of this hidden water ocean and the rich organic chemistry on its surface makes Titan an incredibly compelling target. So we have all these tantalizing clues, but how do we move from strong suggestions to hard proof? How do you see through miles of solid ice? The answer is radar. The word radar is an acronym for radio detection and ranging. The basic idea is simple. You send out a pulse of radio waves and listen for the echo. The time it takes for the echo to return tells you how far away something is, and the strength of that echo tells you what it's like. For peering into icy moons, scientists use a special tool called ice-penetrating radar, or IPR. This technique uses long-wavelength radio waves, which have a unique property. They can travel through pure water ice without being absorbed very much. Rock or salty brine, on the other hand, would stop them. As these radar waves travel down through the ice shell, They bounce off any change in material. A boundary between different ice layers, or pockets of brine, will create a faint echo. But the grand prize, the telltale sign of an ocean, is the reflection from the very bottom of the ice shell. The boundary between solid ice and liquid water creates a massive contrast, which sends back a strong, smooth, and flat echo that's unmistakable to scientists. By precisely timing this echo, we can map the thickness of the entire ice shell. And this is a critical piece of the puzzle. A thinner shell would make it easier for materials to mix between the surface and the ocean below. The surface of a moon like Europa is constantly blasted by radiation from Jupiter, which can create oxidants, compounds that could provide chemical energy for life. If those compounds can get down into the ocean, it dramatically increases the moon's habitability. Another powerful technique is synthetic aperture radar, or SR. This is an imaging tool. It uses the motion of the spacecraft to create a massive virtual antenna, allowing it to produce incredibly detailed, high-resolution maps of a planet's surface. Unlike an optical camera, SAR can see right through Titan's thick haze or the complete darkness of the outer solar system. It works by analyzing the backscatter, how the radio waves bounce off the surface. Smooth surfaces, like a liquid methane lake on Titan, reflect the signal away and appear dark in an image. Rough surfaces, like fractured ice fields, scatter the signal everywhere and appear bright. This allows scientists to map the geology of these worlds in stunning detail. Our understanding of these worlds has been built over decades by robotic explorers. The Voyager missions in the 70s gave us our first close-up pictures. The Galileo mission at Jupiter in the 90s was a game-changer, providing the magnetic field data that pointed to Europa's ocean. And the Cassini mission at Saturn from 2004 to 2017 was a triumph, using its radar to map Titan's surface and discovering the incredible plumes of Enceladus. Now we are entering a new wave of exploration, with two ambitious missions designed specifically to use radar to unlock these icy secrets. First is the European Space Agency's Jupiter Icy Moons Explorer, or JUICE, which launched in 2023. JUICE will tour the Jovian system, but its main target is Ganymede. After several flybys of Europa and Callisto, it will become the first spacecraft in history to orbit a moon other than our own. Its key instrument is called RIME, which stands for Radar for Icy Moons Exploration. RIME is designed to penetrate up to 9 kilometers into the ice of Ganymede, Europa, and Callisto to finally map their subsurface structure and find that ice-ocean boundary. Hot on its heels is NASA's Europa Clipper mission, which launched in October 2024. As its name suggests, this mission is focused squarely on determining the habitability of Europa. Its secret weapon is a state-of-the-art radar instrument called REASON, which stands for Radar for Europa Assessment and Sounding, Ocean to Near Surface. REASON is a dual-frequency radar. It uses a low frequency to penetrate deep into the ice shell, searching for the main ocean. At the same time, it uses a higher frequency to get high-resolution images of the upper parts of the ice. This will allow it to search for one of the most exciting possibilities: pockets of liquid water or perched lakes trapped within the ice shell itself. These could be even more accessible habitats than the deep ocean. So what are the big questions these missions will answer with their radar eyes? First, and most fundamentally, how thick is the ice? Knowing the thickness and how it varies across the moon will tell us about heat flow from the interior and the geological processes at work. Second, where is the water? Beyond just finding the main ocean, radar can spot those potential perched lakes inside the ice shell. These could be crucial targets for a future lander. Third, what is the ice shell like? The faint echoes from within the ice can reveal layers, like rings on a tree, that record the moon's history. This tells us how the ice has flowed and deformed over millions of years. And finally, is there an exchange between the ocean and the surface? This is the key to habitability. Life needs energy, and on Europa, that energy might come from surface compounds created by radiation. Radar can help find the pathways, like fractures or upwelling plumes, that could carry these vital ingredients down to the water below. Ultimately, this all leads to the astrobiological implications. Radar cannot detect life directly, but it is our best tool for identifying and characterizing habitable environments. Confirming the existence and depth of these oceans, mapping the ice, and finding pathways for chemical exchange are the essential first steps. A discovery that Europa's ice shell is thin and active would make it a top-tier candidate for life. Finding subsurface lakes would give us a new, more accessible place to look. Understanding Ganymede's layered ocean will tell us if its water is in contact with a rocky mantle, a process that could provide the chemical nutrients life needs. We are on the verge of a golden age of discovery in our solar system. The JUICE and Europa Clipper missions are on their long journeys to Jupiter, carrying our radar eyes with them. They will rewrite our textbooks, but more than that, they will bring us one step closer to knowing if the spark of life has ignited elsewhere in the cosmos. In the cold, dark, and deep oceans of these distant, icy worlds.